Hi everyone, welcome to the Earth Science Regions Review podcast series created by Hammock's Middle School Earth Science Department. Today we're going to be talking about glacial characteristics. Now, glaciers are a very unique feature here on the planet, very simply because geologists call them rivers of ice and snow. They move very similar to how water flows, and they're all going to be solely based upon the slope of the land. Steeper the slope, faster the movement of this ice and snow. And it all comes down to how much snow is going to accumulate in the upper elevations. So here you can see the Columbia ice field as it enters a larger body of water. Now the glacial movement's very similar to water, except a little bit slower. Water moves faster in the middle, just below the surface. The same thing with glacial ice. And the very reason is very simply because of the fact that there's a lot of friction along the edges of the glacier and along the bottom, so your ice tends to travel faster just in the middle, just below the surface. And again, the velocity of the glacier is solely dependent upon the slope of the hillside. So you can see a bird's eye view and a profile of what a glacier might look like. In the middle, just below the surface, is going to be the key. Now you have a couple types of glaciers. The first type is what we call an alpine glacier. These are found in the upper elevations of mountain ranges where snow is going to start building up. These things get so massive they actually carve a U-shaped valley in the landscape, much like what you're seeing here. The second type is what we'll call a continental glacier, and this is when full continents are covered by ice and snow, and that's going to be Antarctica and Greenland are going to be the two examples. We also had one over top of New York State 22,000 years ago during the last ice age. So there's Greenland, there's Antarctica, and there's a diagram of what the continental ice sheet called the Laurentide ice sheet, what it might have looked like over top of North America 22,000 years ago. Notice that New York State's completely covered. Now you have a couple zones of the glacier. You have the zone of accumulation, the zone of melting, and then finally the snow line. Now when you get more accumulation than melting, the glacier is going to get bigger. When you get more melting than you do accumulation, the glacier is going to get smaller. When melting and accumulation equal each other, that glacier is going to be stationary, means it's not going to be moving, it means that we have reached equilibrium with the glacier. So there's your zone of accumulation, and there's your zone of melting. So glaciers not only deposit, but they'll also erode as well. They're going to transport sediment to a new location. And some of the erosional features are as follows. You can get cirques, which are bowl-shaped features at the top of mountains where snow builds up. You can also get what are called arêtes, which is the rock that separates two cirques. Sometimes you can get multiple cirques in a hillside or a mountainside, and you get what's called a horn. And a horn is a very sharp peak on the mountain slope, and the most famous is the Matterhorn Peak in Switzerland. You also have striations. Glaciers are like big pieces of sandpaper. As they pick sediment up, they're going to ground out the rock that's underneath it with the sediment that's picked up. So the striations are basically going to be parallel grooves that are carved into the bedrock by the sediment that is picked up. The great thing about striations, they show the direction of ice flow. And in New York State, that's going to be in a north-south direction. So here's your picture of what striations might look like. Notice the parallel grooves in a north-south direction. So we can also get depositional features as well. Some of the depositional features include till, which are also called moraines. This is the large collections of unsorted material. So you see the unsorted, no organization to the sediment at all. Sometimes those moraines are at the end, called terminal moraines. Sometimes they're on the side, called lateral moraines. And sometimes they're in the middle, called medial moraines. Sometimes those glaciers can produce hills as well during their deposition. Now some of these hills that are unsorted sediment are what we call drumlins, and they're somewhat teardrop shaped in nature. The great thing about these drumlins, they also show the direction of ice flow, and in New York State, the tip of the drumlin points south. So here's an actual drumlin itself from up above, and also a profile. Continuing with the depositional features, you can get outwashed plains. When glaciers start to melt, they're going to start to organize their sediment at the base of the glacier, called an outwash plain. So all that sediment is somewhat sorted in nature. Continuing with the depositional features, big chunks of ice that break off in the water are called icebergs. Big chunks of ice that break off on land are called kettles, so they leave a big dent in the ground. Sometimes those kettles get filled up with water, and they're called kettle lakes. And finally, you get something called an erratic. These are going to be monstrous boulders left over from the glaciers. Glaciers have a tremendous carrying power, so some of the deposition that takes place with these sediments are quite massive in size. Now, there's no real understanding about why we have these ice ages, but Milutin Milankovitch came up with a three-part theory, which is kind of the leading theory behind why we think the ice ages occur. The first one is what we call obliquity, which just means the axial tilt of the planet changes from 22 degrees to about 24 degrees every 41,000 years. That'll ultimately change the amount of insolation on the planet. Precession just means that the axis has a wobble, that every once in a while it will change from pointing to Polaris to pointing to a star called Vega, back to Polaris, back to Vega. Again, every 25,000 year cycle, again, changes the angle of insolation. And finally, the eccentricity, which basically changes the shape of the Earth's orbit from being somewhat circular to being elongated, ultimately changing the amount of insolation from the sun as well. So this three-part theory gives us an idea about why our ice ages actually occur. Now, that last ice age was very important to us, very simply because it happened about 22,000 years ago during the Pleistocene epoch. And we believe, because of the shape of the landscape right now, that the ice might have been upwards of about a mile thick. It brought in a tremendous amount of transported sediment from northern Canada, and it did create a couple features on New York State, which includes Long Island, the Finger Lakes, and the Great Lakes. So here's just an idea about some of the features. The Great Lakes, two of them border New York, that's Lake Ontario and Lake Erie. All of them are U-shaped in nature. The Finger Lakes, again, are U-shaped in nature. Long Island is partially unsorted material, such as a moraine. There's actually two moraines in Long Island, the Ronkonkoma moraine and the Harbor Hill moraine. Part of it is sorted in the term of outwash, because part of Long Island had to form when the glacier melted, which produced outwash, which is sorted. And then finally, the Hudson River Valley and the Hudson River are somewhat U-shaped in nature as well. Now, just remember that glaciers are going to give you unsorted sediment. They're going to give you unlayered sediment unless the glacier starts to melt. If the glacier starts melting and you get glacial meltwater, then those sediments will be sorted. So that's it for now. We'll talk to you soon.